Hello. In the previous video, I started with the topic of nonlinear regression or polynomial regression, and I have explained the idea, the motivation, and the theory behind nonlinear regression. In today's video, I will show you how we can compute the list of coefficients of our nonlinear model using either a closed form approach or gradient descent algorithm. And in the third part of this video, I will cover the topic of multivariate nonlinear regression when we have more than one predictor in order to build our model. So starting with the closed form approach, we end up last video with computing the derivative of cost function with respect to each coefficient w, and the second step after computing these derivatives is to set these output derivatives to 0, and we will try to arrange and simplify this equation. So first of all, we will delete the term of minus 2 over n, and we arrange the equation in a way such that we put the term that contains the target variable w in the left hand side of the equation, and the terms that contain the coefficients w0 and wp in the right hand side of the equation. And we try to simplify it once again by sending the w0 multiplied by n outside the sigma notation, plus wp multiplied by x super I to the power of 2p inside the sigma notation of b, moving from 1 to capital B, where capital B expresses the level of or the polynomial degree of our hypothesis function. The generated system of equations can be transformed into a matrix form such that we have the left hand side represents a matrix of the target variable multiplied by the predictor variable, and in the right hand side we have two matrices. The first one represents the vector of coefficients we are trying to find, and the second matrix represents the matrix of predictor x that we already have as an input of our training data. So using this notation, we can easily discover that both the left hand side matrix is known, as well as the predictor matrix is known. The only unknown matrix in this expression is the list or the vector of coefficients w. And if we simulate this system of or this matrix form into the form of capital B equals w multiplied by capital A, we can easily find the values of coefficients w in a closed form by computing a to the power of minus 1 multiplied by b. So this is the way we can calculate the list of coefficients in order to find our nonlinear model in a closed form approach. Moving to the gradient descent algorithm, we use the same gradient descent algorithm we have used and talked about in when we were talking about the linear regression topic. It has the same structure. The only difference here is regarding the update step, which is represented here in the 9th step of the algorithm. For each coefficient value wp, where p is moving from 0 to the degree of polynomial you are looking for, we use this update expression here. We say that the updated coefficient equals the old value of coefficient minus eta, the learning rate, multiplied by minus 2 over n multiplied by the derivative of this of the cost function with regard to the current coefficient we are calculating, and after a certain number of iterations we can approach a list of coefficients that minimizes the error function to some extent. So this is how we use both approaches, the closed form and the gradient descent, in order to find the list of coefficients and find our nonlinear model. Now I will move to the topic of multivariate nonlinear regression, and this is also a nice topic to talk about, because we in many cases in real life we face data that have more than one predictor, and we need to make use of all of our predictors, not only a single predictor but more than one predictor, in order to enhance and improve the outcome of our model, of our statistical model. So here I am giving you an example of two predictors, and of course you can expand it as you wish, as your data contain as many features as you want. But for simplicity, I will give an example of two predictors here. If we want to build a nonlinear regression model using these two predictors x1 and x2, and suppose we have this hypothesis function w0 plus w1 x1 super I plus w2 x2 super I plus x3 x1 super I square. So here the function starts to be non-linear, plus w4 x1 super I x2 super I plus w5 x2 super I square. So we have a multivariate non-linear function, and we want to find the list of coefficients of this particular function. So a good turning out of this complexity is to use some temporal vector, we call it here z, where each value of this new temporal vector corresponded to a term of each predictor in our hypothesis function. So here, for instance, if we have 5 terms here, 1, 2, 3, 4, 5, we substitute each predictor term with a z term, such that we have here the z1 corresponded to x1 super I, the z2 corresponded to x2 super I, and so on. And we do this transformation just for simplicity, in order to be able to write our equations more easily, either in the closed form or in the gradient descent approach. And of course we can always substitute the temporal values of z vector with the actual predictor values. So we can, after doing this transformation, we can rewrite our regression function in this more simple and easy to read form. And once we build this equation, we can instantly use the closed form function or the closed form approach in order to find the list of coefficients we are trying to use. First of all, we build a matrix of predictors in this form. It will take the number of rows equals to n, where n represents the number of observations we have, and we will take m plus 1 columns, where m represents the number of predictor terms we have into our equation, and we always increase it by 1 because we reserve the first column of this matrix equals to 1 to correspond to the w0 coefficient, which has nothing to do with the predictors. Afterwards, we also build our vector of target variables of our training data, moving from 1 to n with the target variable y. And after obtaining these two matrices, we can easily compute the corresponding list or corresponding vector of coefficients w using the expression x transpose multiplied by x all to the power of minus 1 multiplied by x transpose multiplied by y. If you calculated this expression, this will generate the corresponding list of coefficients that best fits your data into the multivariate nonlinear regression model. We do the same also with the gradient descent algorithm. The only difference between this case and the univariate gradient descent algorithm is that we here again use the notation of z in order to simplify our equation. So we use it with w0 and also with wj, where j starts from 1 to p. And because we have 5 terms of z, or the length of the z variables equals to 5, so the j here moves from 1 to 5 with each coefficient multiplied by its corresponding predictor value. And this is the way we can use either a closed form or gradient descent algorithm in order to find the best nonlinear regression model of our problem if we have more than one predictor. In the description below, I will leave the link of implementation, of Python implementation of all of these methods, and I encourage you to run it yourself and try to understand better and visualize better how these approaches are working, and try it with different data sets such that you have a better understanding of the topic. Thank you for your time.